Hello, everyone. This is a video on 7.2, which is sets. So learning objectives for this section, basically we're going to identify and use the set for properties and set notation, perform set operations, and solve applications involving sets. So to begin with, I just wanted to give you a question prompt to make you think about what we're going to be doing in this section. These are some of the problems from question 75 through 88. You'll find out that basically this notation means the number of whatever set you're talking about. In this case, is the number of freshmen. So you'd actually end up summing up both these and you get the number of freshmen. That's what that set would mean. Now we'll talk about what this symbol means, which means intersection, and this means union. So you'll find out that intersection is basically the way of saying and this is meaning or. We'll do a couple of examples here in a little bit, just to make that come clear, and we'll return to this application at the very end. So basically, we'll talk about the symbols that are used and the concepts of set theory. The definition of set is any collection of objects specified in such a way that we can determine whether a given object is or is not in the collection. Some notation. If you note that a set, we're going to use capital letters, and we use smaller lowercase letters to denote an element of the set. So in other words, E is an element of the set A. Is how we look at that E symbol right here. That's how we denote that. So for example, if the set with A was all negative numbers, E could be -2, and 2 is an element of the set of negative numbers. So one way you can look at it. And then also if you put a line through it, just like if you have the not equals symbol, in this case, this means it is not an element of the set A. So for example, if the set A was still negative numbers and E was +14, for example, that would not be an element of the set of negative numbers. So you can also write out sets with all of their elements like this, with the curly brackets and the values that are in there. This is called the rostering method. We can do that as well. So the null set is an example of where there is no values that are in the set. So for example, what are the real numbers of the solution of the equation x² + 1 = 0, right? So if we moved 1 to the other side, we'd have -1. So x² = -1. So what are the real numbers that satisfy that? And the answer is there are no real numbers that would satisfy that, right? There are no real number solutions to this equation, since no real number squared added to 1 can ever equal 0. We represent the solution as the null set, and you can write it as just the curl brackets with nothing in it, or you can write it as 0 with basically a line through it. This is generally how people write it. They write this as basically the null set. You might also hear it as referred to as the empty set. Set builder notation is more commonly used as you go through your math problems or different applications, or as you go into more complex things with theory and proofs. So in this case, this set A is equal to X such that X is a letter of the English alphabet. So in other words, whenever you see this, it means that it's such that, or that it is a part of that set, or whatever you might be saying to basically denote that whatever variable, X, for example, is a letter of the English alphabet. So this, by the way, is just a representation of this. This means it could be A, it could be B, it could be C, it could be D, it could be E, it could be F, all the way up to Z. Just so you know, it's not that X, such that X is a letter. It's more that's just saying a way of categorizing all of the values that could be there. So, for example, X such that x² is equal to 9 is the set that we're looking at. Another way that we could write that set is that 3 and -3. A subset is basically just a smaller set from the big set, or it can even be the same exact set, as you might find here in a little bit. But basically, A is a subset of B if every element of A is also contained in B. So for example, A is a subset of B. For example, a set of integers is a subset of the set of real numbers, right? We can look at that way. I could also say A is the set of negative integers, and B is the set of real numbers, or I could say all integers, whatever you might think. A formal definition: A is a subset of B, means if X is contained in A, then X is contained in B. The reason why these definitions are important is that if you do theory or proofs, basically that's how you can show that basically an element is in A and an element is in B as well, and therefore A is a subset of B or whatever it might be. Claim the null set is a subset of every set. To verify the statement, pick any arbitrary set and then apply the definition of subsets. And you could say X is an element of the null set, and then X is an element or is contained within the set A. You can do that basically. Since the null set contains no elements, the statement if X is an element is false. We know that if P, then Q is true. If P is false, since P is false, we conclude that the conditional statement is true. Therefore, the null set is a subset of every set, right? That is basically a proof right there. I know it doesn't say proof and then shows all this, but that's basically what that just did. And that was part of 7.1 coming in with 7.2. Feel free to pause that one and go back to it. Might be worth looking at that and reading that one more time. The number of subsets. So list all the subsets of the set A. So we have bird, cat, and dog, and these could be pets, right? For convenience, we'll use the notation B, C, and D to represent set A. So if we wanted to write the subsets of them, so I'll make this a little bit bigger over here. And we're doing 7.2, right? And 2355. So again, writing down some of those things to make sure my notes are a little easier to follow for all of us, right? You might want to do that too with your notes. So we have the set A is B, C, and D, right? Another subset we could have is we could have just B, just C, just D, right? We could also have the set B and C. We could also have the set B and D, right? We could also have the set C and D, right? We could also have the empty set. And we can even have the set B, C, and D. Those are all the subsets that we can have of basically that. So there are 8 total subsets that you could have. The empty set is one of them. The actual set A is a subset of A as well, which sounds kind of weird or redundant, but that's by definition. So B, C, and D, so you have 2 subsets right there. Then you have B and C, B and D, C and D, so now we have 5. And then we have 6, 7, and 8. And there you go, those are all the subsets. Now we need to get into the definitions of things like union. So union is basically set A and set B. And what we'll talk about it is basically if an element X, such that X is either an element contained in A or X is an element contained in B. And so if you wanted to think about a Venn diagram usually is a box, and then you have circles drawn in it denoting what the groups or sets are. In this case, it would be all of A and all of B. So it's either in this one, or it can be in both. And that's why both areas would be shaded. And that's union. This symbol means union. So it's kind of similar to that disjunction, the V that you saw in 7.1. So an example of a union, the union of the rational numbers with the set of irrational numbers is the set of real numbers, right? So it's either A or B. And basically together, that is the set of real numbers. And notice that there is no overlap with rational and rational numbers. So now the intersection is just like it sounds. It's the intersection. Basically, it's the intersection of set A and set B. And that means there's this overlap right here. So you have this symbol, which means intersection, and X such that X is an element of A, and, notice and is the key word here, X is an element of B. And that means that it has to be in A and B. And so that's why it's this piece right here. So The intersection is a more exclusive thing because it only includes that small sliver of overlap. If we were to go back a slide, you'll notice that there is no intersection with the irrational and rational numbers. So that would actually be considered the empty set if you were to go through and do that. So if two sets have no elements in common, they are said to be disjoint. So sets A and B are disjoint if A intersect B is the empty set. An example is the rational and irrational numbers are disjoint. Can you guys think of other ones? So I'll give you like 10 seconds. How about negative numbers and positive numbers? Is there any overlap with them? The answer is no, there is no overlap with them. So they would be disjoint as well. So this set of all elements under consideration is called the universal set, and this will be important when we start doing probability related to this. So for example, when discussing numbers, the universal set may consist of the set of real numbers. All other types of numbers, integers, rational numbers, irrational numbers, are subsets of the universal set of real numbers. So the reason why it's important to understand the universal set is when I talked about that Venn diagram saying a box around it, not A and A, that would be the universal set, means all of the things under consideration. So when you see this little prime or asterisk, not asterisk, but prime up there, or apostrophe, if you will, basically what it means is that it is the complement of set A. So a lot of times you might say it's everything that is not contained in set A. That would be the complement. So for example, the complement of A is equal to X is an element in the universal set such that X is not an element of set A. Basically means, right, everything that's not A is the complement. So for example, if you were to say the set A is people with brown eyes, then A complement would be the set of everyone with not brown eyes. So like blue eyes, green eyes, black eyes, you know, whatever. And here's an application. A marketing survey of 1,000 commuters found that 600 answered, listened to the news, 500 listened to music, and 300 listened to both. Okay, let N be the set of the commuters in the sample who listen to the news, and M be the set of commuters in the sample who listen to music. Find the number of commuters in the set N and M prime. In other words, remember that's intersection, and this is not M. The number of elements in set A is denoted by NA. So in this case, we are looking for N, and then parentheses N prime. I'm going to make this viewable for you guys, and we'll write down all those things. Oops. It's right here. So the study is based on 1,000 commuters. So this big U, and that includes everything in this box, is 1,000, okay? Now, when we go back here, if we go back 1 second, we have 300 listen to both. So 300 listen to both, that would be this intersection right here. And that's the 300 that we're talking about, that red part, right? The set N news listeners consists of the green part and the red part. So in other words, news is this part and the red, green and red. And the music would be the blue and the red. And now we can figure out each component's piece of what they are. So 300 listen to both. 300 plus that 300 give you 600 that listen to the news. And 300 plus the 200 give you the ones that listen to the music or both. So 200. So if you add 300, 300, 200, 200, you get 1,000, and that should make sense. So in this case, we're asking for the number that listen to the news and do not listen to music, which would be 300, which is just this piece right here. So let's return back to this application problem that I have for you guys. Now I think you guys have a little more of the terminology. So we'll do one for real basic cases. In this case, we'll use a table instead of a Venn diagram. You can draw a Venn diagram if you want. That works as well. So in this case, I'm going to rewrite that table out. So I have arts and sciences, and I have business, and I have freshmen and sophomores, right? And so I have that table drawn. I'm going to draw in all those values. And so I have 19 for freshmen in arts and sciences, 66 in business, and 14 sophomores in arts and sciences, and 21 in business. Now, one of the things is when you construct these tables, you will want to go and sum them up. So sum up the columns and rows, so that way you have that for later reference. So 19 and 14 should give you, I think, 33. And 66 and 21 should give you 87. And 14 and 21 should give you 35. And 19 and 66 should give us 85, I believe. Yeah, 85. And one thing we can always do to double check that our math is correct is if you add these two together, they should equal this as well. So in this case, by the way, we know that the universal set should be 120. So that'll give us 10, that'll give us a 4, that'll be 120. That'll give us 120 as well. So we did that correctly. And this is the grand total, right? This is the number in the universal set is equal to that, okay? So we have that piece. Now, if we wanted to do number 75, we have the number of freshmen is what we're looking for. Well, that's this right here, 85. If we want to do 76, that's the number of sophomores, which is sophomores, 35. Okay, right? Keep in mind, this is the total, right? So total. So you guys should get pretty comfortable with dealing with these tables, given we've done so much with it. So let's now turn our attention instead to do like 81 and 82. And then we'll do 83 and 84. So 81 asks us for the number of business intersect freshmen. So that means business and freshmen. So if you're looking at this, you're looking at this business and freshman and symbol right here, which would mean it's 66. Now, 82 has the number of business and sophomore. So business and sophomore is 21. How about this now? Let's find one where we have the or statement here. And so let's do number 85, which is the number of business or freshman. So business or freshman means business is this or freshman. So we'd have 19, 66, and 21 added together. And that'll give us our total. So you could add 87 and 19 together. So in other words, 20 plus 86, which would be 106, I believe. Yep. The other way that you could see that, if you wanted to figure out that, everything that is not that would just be 120 minus 14. And that'll give us, sorry, everything that's not that is 14. So if you did 120 minus the 14, will give us the 106 as well. It's kind of neat that way as well. 86, we have the number of business and sophomore. So business and sophomore is this, which is going to give us 101. So that's basically 7-2 in a nutshell. And these are the problems that I have in the text. And again, you can find the PDF text copy of these problems as well. Let me know if you have any questions.